Great. All right, I'll get started. So yeah, thanks for the introduction, Michael. So I'm a professor at CU Boulder, and this presentation is going to be about how Julia has impacted my research, and I guess kind of my journey into using it more, and why I think it's useful and how I've enjoyed it. So my research is in kind of sequential decision making under uncertainty, and this happens throughout the world around us. You know, we're constantly making decisions, and we want machines to one day be able to make some of those decisions for us or work with us to make better decisions. So one example might be driving an autonomous car. The car has to decide where to maneuver in order to get you to the destination without hitting anyone or being unsafe in other ways. Another one that's, you know, very relevant right now is, suppose we have a pandemic disease going on. How do we manage the different policies? That's a series of decisions that we have to make under a lot of uncertainty. You could also think of like a personal assistant, a Google Home type thing. It has to decide how to assist a human in the home environment. Or you might even think of like a cancer treatment or robots building, manufacturing. In this picture, there's no humans there, but what we really ideally want is for humans to be working right alongside robots and to be able to kind of assist each other. Or another place might be in space, where you might have like a 10-minute or longer communication delay between anything a human can communicate to the robot. And in that case, the robot has to be autonomous and make decisions on its own. So we can formalize these sequential decision problems in a variety of ways. The simplest kind of concept to get is a Markov model. So in a Markov model, there's a state space, which is the set of all possible states that the world can be in. In this little case that I have here in this picture, the states are just 1, 2, and 3. And then transition probabilities, which indicate how likely it is for the system to transition between two states. So in state 3, you have a 10% chance of going to state 1 and a 70% chance of coming back to the same state, and a 20% chance of going to state 2 in this example. But in that case, there's no decisions to be made. So that formalism isn't enough for us. So we can upgrade to what's called a Markov decision process. Now, in a Markov decision process, you have the same state space and transition probabilities, except now we add different actions that can be taken in each of the states. And these actions change the probability of transitioning between states. So by taking these actions, you can kind of guide the state to an area that you want it. And the way that we encode kind of the desirability of different states is through a reward function that maps the states and actions to a real number, which is the reward. And that's these little +5s, you know, or ±10s coming off of these transitions. So there's going to be a little math. It looks intimidating, and these slides were taken from my PhD dissertation originally, so I made them, you know, kind of intimidating looking on purpose, just so I wouldn't get any flack from the professors. Or I shouldn't say that. I should say I made them complete. But anyway, so the objective of a Markov decision process is to maximize what's called the value function by choosing a policy pi. And this policy maps each state to the optimal action to take. And the value is the sum of all of the future rewards. So we want to choose a policy that maximizes this value. Now, this is a really difficult optimization problem because it has to take into account not only the decision at the current time, but also all of the decisions in the future. But fortunately, we have some tools to deal with that efficiently. So this is one of my favorite equations. If you're in in this field of reinforcement learning or decision making under uncertainty, this is probably one of your favorite equations. It's called the Bellman equation. And this breaks the original value function equation down into two components, the reward at the current time and the reward for all future time integrated into this V star value function. And this is a much easier problem to solve because this equation, or rather, I should say, this is a good equation to use because it only involves the current time and the time at one step into the future. Now, it turns out that this equation is a contraction mapping, which means that we can iterate on it and solve for the optimal value function in a finite amount of time if the state and action spaces are discrete. And then another important quantity to be aware of is what's called the Q value function. And this is often what you see in reinforcement learning contexts. So this Q value is equal to the current reward plus all future rewards, given that you start in state S and you take action A. So if we can find the Q values for the problem, then we've solved the problem, because we can our policy can be just to take the action that has the maximum Q value associated with it at the current state. So one way to do this is to calculate the Q value for all of the states and actions offline. Before you even get into the environment that you're interacting with, you can solve the problem offline by finding these Q values. Another way to do it is what's called Monte Carlo tree search. So in this approach, you take your Markov decision process, you reform it into a tree. As you can see, all the same nodes are there. They're just moved around a little bit until you have this tree where the downward nodes are further into the future in time. And the way that Monte Carlo tree search solves the problem is by estimating the Q values at each of the action nodes. And then if you're in state 3 and you've constructed this tree and estimated the Q values for action A and action B, then you just choose the one with the highest Q value. And that's guaranteed to be the optimal solution if this tree has calculated those values correctly. There's a lot of difficulties with this, but the solutions are kind of detailed. If you just understand what this tree is, then you'll have enough to kind of understand this talk. But there's one of the difficulties is that in real life, you often don't actually know the full state that the world is in. So you can see some things with your sensors, but in the real world, you can't see everything. So in that case, instead of a Markov decision process, we have what's called a partially observable Markov decision process, or POMDP. So now you can see this figure looks exactly like the Markov decision process figure, except instead of having the actual state that we're in, we have these question marks because we don't actually know what state we're in. Instead of being able to observe the state exactly, we have an observation at each time step from an observation space. And these observations are distributed according to an observation probability distribution Z. So let's talk about what in the real world might be observable states and hidden states. So in this autonomous driving situation, it's pretty easy to measure what I like to call the external states of the system. So the kind of position, velocity, things that you can measure with your vision sensors of the car. But there's also internal states that we can't measure that are actually important for decision making. And those might be something like the intentions or dispositions of the driver, or whether they're focused on the road, whether they're distracted. Because an autonomous system should behave fairly differently based on what the intentions of the other vehicles on the road are. And so in this POMDP case, we perform what's called the sense plan act loop. So we have the environment here. At each time step, we get an observation O of the environment, which might include, for example, the physical states of the car. And then that observation and the previous observations are fed into what's called a belief updater, which integrates all these beliefs integrates all the observations using Bayes' rule, and calculates the probability of what hidden state the world might be in. So, for example, we might conclude after observing the car for a while that it's more likely to be aggressive than timid, and that can help us plan for the future. So planning looks a lot like the MDP case, except that we now have to plan over the possible different beliefs that we'll encounter in the future instead of just the possible different states, because we're never going to know exactly what the state is. So this decision tree has, again, squares correspond to actions and circles correspond to beliefs. But now instead of those circles corresponding to states, we have these little orange things, which could be kind of probability density functions that correspond to different beliefs that we could encounter in the future. But again, by creating this tree and calculating the Q values, we can choose the best action for the long term, and then take that action, the environment changes, and then we go through the loop again. So most of my research involves figuring out what to do inside this planner block. How do we, given the belief, given a probability distribution over the true state of the world, how do we determine what the best action is to take? So now I'm going to go back a little bit and talk about my journey with Julia. So in 2011, I have this tweet that I found last night, which was sent at 1:25 a.m. You'll notice I actually remember this day because I sat down. I was like, I knew, MATLAB, I knew C++. I used both of those a little bit, and then I sat down and I was like, I'm going to learn Python because it looks pretty cool. And by 1:25 a.m., I was pretty satisfied. I thought Python might be the programming language I've always wanted. And I kind of got into that. I used it when I could. So here is the post from 2013, a couple years later, where I am interactively debugging Python code that's running inside a C++ application that I wrote that was launched via MATLAB because I needed the plotting, and all my other master students' friends, used MATLAB. So you can't see it in that picture, but if you zoom in there, you'll see I have, some C++ code from this set option function in the helicopter namespace. And then I'm running PDB inside this MATLAB GUI window. And I was pretty proud of this. You can see I liked my own post here. So I thought this was, as good as it gets. But pretty soon I started to realize the, weaknesses of this. I don't have a social media post for this, but I distinctly remember in 2014 when I had to do numerical integration of the forces on the drag forces on a solar panel of a satellite. And I wrote up a Python function to do this, and it took forever. So I, had to Google how to write C extensions for Python, because since Python is a interpreted language, it just wasn't fast enough for those inner loops to be Python functions. So I was, kind of looking for an answer for this. But luckily, there were other people working on other things at this time. So in about 2011, this was when I was first discovering Python, my advisor, Michael Kokendorfer, my future advisor, I didn't know him yet. This is him testifying to the Senate, I think, about some UAV regulations or something. He was working on improving a system called TCAS, which is short for Traffic Collision Alert System, something like that. What it's designed to do is to help airliners avoid each other. And what TCAS consists of is a bunch of hand-specified pseudocode rules that look like this. Literally, this is taken from the TCAS specification that try to prevent aircraft from running into each other. So, for example, if these two aircraft are about to collide, the radar detects that they're about to collide, and then it gives one of them a climb instruction and one of them a descend instruction. So in this case, it told the aircraft on the left to climb and the aircraft on the right to descend. Unfortunately, the aircraft on the left descended, and so it resulted in a crash. And so they wanted to get a more robust system in place. And so they introduced this thing called ACAS-X. Now, ACAS-X takes this situation, models it as a POMDP, where there's some uncertainty in the physical state of the aircraft, but also in whether the pilot's going to respond or how the pilot's going to respond, if they're actually going to respond to the instructions of TCAS. And they combined it with Julia, and they got out this system called ACAS-X, which is much better. If you look at this diagram closer, you'll see an example of how it's better, but I won't get down into the weeds of that. And the interesting thing about this was that they used Julia both for solving this POMDP optimization problem, but Julia has this unprecedented combination of speed and clarity. So they actually also use Julia directly in the specification that's written up in the official document that defines how this is supposed to work. So, previously this would be pseudocode, but Julia is concise enough and expressive enough that they decided to use it both for the optimization and the specification document, which is pretty impressive, I think. So we decided during my PhD, one of the things that I did was we decided to build on this a lot because this Julia software that my advisor wrote for ACAS-X was, pretty much built for this one thing. But we wanted to build a software suite that could handle any POMDP. And so we built this package called POMDPs.jl, which we're still building and improving on to this day. So the idea is that there's kind of three people involved in this process of solving a POMDP. There's the problem writer. There's somebody who writes down the actual real-world physical problem in code. Then there's the solver writer who writes a program to solve that POMDP, and then the person running the experiment. And these three people, or three roles, sometimes it's the same person in two roles, but they need to communicate. And we wanted a flexible interface for these people to communicate that had no speed consequences. And Julia turned out to be a good language to do this with. But there is a lot of challenges to overcome to write this POMDP software. So the first one is that POMDPs are computationally difficult. They're actually a p-space complete class of problems, which means that there's not going to be any magically efficient algorithms to solve them. So we need every ounce of computation that we can get. Julia is, of course, very good at this. I won't go too much into the details, but if you're here, you've probably seen the benchmarks that say that Julia has performance comparable to C. In my experience, it actually usually ends up performing better because it allows the programmer to iterate so quickly that they can try out different ideas that they wouldn't have had time to try and see. And then also the other evidence of this is the Celeste project, which put Julia in the petaflop club alongside of C and Fortran, et cetera. So that kind of is a good thing for handling the first challenge of writing POMDP software. The second problem is that it needs a huge amount of flexibility. So there's a huge variety of problems, solvers, and different heuristics that you might want to use to solve a POMDP. And I'll just focus on one kind of, so like some examples of this are some problems are continuous, some problems are discrete. There's like fully observable MDPs or partially observable POMDPs. But I'll just focus on this one distinction, which is generative or explicit. So an explicit problem means that we have all of the probability distributions explicitly defined for us. So we can say from state 1, there's a 50% chance of going to state 2, for example. Whereas a generative in the POMDP literature, this has a generative, the word generative has a different definition in the wider machine learning community. But for POMDPs, generative means that there's a black box model where we can put in a state and action and get out the next state, observation, and reward. But we don't explicitly know what the probabilities of those are. And so there's been attempts to do this before, kind of unify this or write software for both of these explicit and generative cases. This is actually a previous C++ framework called APPL. I'm not sure if their website still says this, but it did a while ago. It said, so they have 3 packages and they work on 3 different kinds of problems. And you can't take, so if it's, in some cases you can do this, but in most cases you can't take a problem definition from one of these solvers and use it on the other. And their website actually says at the moment, these 3 packages are independent and maybe one day they will be merged into a single coherent framework. And I'm here to tell you that this today is that day, and POMDPs.jl is the single coherent framework that they can all be merged in. So the way we ended up solving this is by having both an explicit and generative interface that you can program problems in and that solvers can use. And if you program the explicit interface, it will automatically give you a generative definition that your solver can use if that's all it needs. And so this is possible in a lot of languages, but it took a lot of experimenting and changing stuff around in order to do this correctly. So we think Julia was a really good choice for this. Moreover, here's kind of an example of the difference between a C++ version and a Julia version. So these 3 algorithms are the basic algorithms of a solver called the despot solver. And these algorithms programmed up in C++ look like this. You know, a lot of lines. It's, you know, not too bad. These were the original authors of the paper, and they programmed the algorithm, and it looked like this in C++. And then in Julia, it looks like this, and it has roughly the same performance. So as you can see, there's a really clear mapping between the pseudocode that was in the paper and the actual algorithm in Julia, which is, we think, a really big advantage because it makes it a lot easier for people to read the paper, come through and, you know, modify the algorithm, try different things out, understand how it's working, understand why it doesn't work. So looks like I'm a little low on time, so I'm gonna speed through some of this. So we actually, the contribution that we made is to improve algorithms in ways that we probably wouldn't have been able to in another language. So, or we wouldn't have known that we needed to improve them in this way. So like I said, you can use Monte Carlo tree search on POMDPs, but it's much more efficient if instead of using explicit distributions, you just use particle filters to represent the belief. Now, we coded this up, and with POMDPs.jl, this is old code. The new versions of it are much more concise than this. But we were actually able to make this handy little tree explorer. And not very many people do this with their C++ algorithms. But we can, you know, play around with this. And these trees get very complex. You know, they have thousands of nodes. And this actually allowed us to, you know, look at it much more closely. Now, this, obviously, this viewer is written in JavaScript, so you could have done it from a solver written in any other language, but the kind of flexibility of Julia allowed us to do this in a much easier way. So what we found is that actually on continuous spaces, we have this problem where the if you have a continuous observation space, you get this nice tree for the first layer, but after the first layer, it explodes. So you have 574 children. And this width on the tree is actually really bad because it means that there's no depth to the tree. So after 2 steps, it just dies out. So that's a huge problem. So that's what this old algorithm called POMCP does in continuous observation spaces. So we modified it into this algorithm called POMCP with double progressive widening, which solves that problem of the tree being too wide and turning into a bush. But it actually introduces another problem, which is called particle depletion, where there's only one state particle in each of these beliefs. So that was actually really tricky to figure out. And I don't think we would have figured it out except that we had this nice visualization tool and we could easily interact with the Julia code as we were executing this algorithm. So the new algorithm is called POMC-POW, which uses weighted particle filtering. And so yeah, Michael, I'll be done in less than 3 minutes. This is what it looks like on a multi-car scenario. So each of these, this is a simulation of cars driving down a highway. The green car is the car that we're controlling. And then the other cars on the road all have varying amounts of aggressiveness. So the red cars are more aggressive, the blue cars are less aggressive. And these lines are our predictions of what they would do if they were aggressive or timid. So right now, this purple car, we don't know whether it's aggressive or timid. So we have varying red and blue predictions about it. But as we go along, we can collect information about the cars and get more accurate predictions of what they're doing. And so these white lines are our potential plans that we're considering executing. And the goal in this case is to get to the left lane within 1,000 meters. So as you can see, this X line is getting up about 800 meters. And just before 1,000, we actually make it to the left lane successfully. And so we actually did a ton of experiments with this, and we found that the POMC-POW algorithm was able to reduce the number of unsafe situations by 50% and actually increase the number of successful times that it made it to the left lane by 50% as well. So this was a pretty successful application of a new algorithm that we developed using the insights that we gained by programming this in Julia. A couple other new things that we're doing. So one of my students has been investigating differential games. So in this case, there's no longer a POMDP, but there's actually this game situation. So we have some continuous dynamics, and each player has their own cost function, and they are all simultaneously trying to optimize it. So this is instead of an optimization problem, this is a game. The problem is that even if we know all of the cost functions of the other players, there's ambiguity about which Nash equilibrium they're playing for. So you can think of this as if you're walking down the hall with someone, there's two equally good solutions, you going to the left and them going to the left, and then you going to the right and them going to the right. But you don't know which one they're thinking. So there's that kind of uncertainty. So we approached this problem using a particle filter. And so a particle filter involves doing hundreds or thousands of simulations of the world and seeing which ones align with the observations you actually have seen. But for this case, each of these particle simulations involves solving one of these differential games. And fortunately, Julia was fast and flexible enough for us to implement this fairly easily and actually run hundreds of these differential games simultaneously in real time. And then the last kind of thing that I'm actually working on right now is dealing with continuous action spaces in POMDPs. So if you have these trees that you're using to solve POMDPs, they work great with discrete actions that you can choose between, but what if they're continuous? And our hypothesis is that we could use gradient information to make small updates to these actions rather than only choosing between big discrete actions. And I actually, unfortunately, just found out yesterday that someone kind of beat us to this. They just published this paper in 2020 earlier this year at AAAI called Monte Carlo Tree Search in Continuous Action Spaces with Value Gradients, which is what we were thinking of doing. But I'll point out that they say a big issue with this is that it requires a white box model of the transition function and reward function to compute the gradients that they need, which is usually not accessible. But I guess I would disagree with this and say that if you're running Monte Carlo tree search online, it means that you have a simple enough model to do thousands of simulations. And when they say not accessible, it often means because they have a model that's written in a language that is hard to get into and find these gradients. But with Zygote, this is actually done in a single line. So we're actually working on this right now, how to auto-differentiate the model in real time as we're doing this Monte Carlo tree search. And we don't have good results yet, but we're getting there. And I think this is really promising and shows kind of the flexibility of Julia to do this fast online computation. And it just works. Like, we used our old models and just used Zygote to differentiate them. And it was able to do it. So I've had a lot of success with Julia so far. It's been a lot of fun to use. Yeah, it's a great tool for the research that I do. I also wanted to acknowledge my collaborators and then say thanks for inviting me to give this talk. And if you have any questions, let me know. Thank you.
Thank you so much, Zach. That was amazing. I'm hearing echoes now. Okay, so why don't we just open it up for a Q&A? Any questions out there for Zach?
I have a quick question. How would you say that this compares with, say, something like OpenAI Gym? And is there a way that you can interface with environments that have been written in OpenAI Gym?
Yeah, so that's a really good question. So OpenAI Gym is written where in a way that the environment encapsulates the state, and it's opaque to that. Whereas in let's see, I'm trying to think if there's a way that I can show quickly what a model in PalmDPs.jl looks like. So here's an example of the mountain car problem in PalmDPs.jl. And so it's pretty concise, and this actually gives it a way to render render the environment in only a few lines. But so what PalmDPs.jl does is it actually separates out the state and the dynamics so that you can interact with both. Whereas in a what's it called, OpenAI Gym environment, the state and dynamics are all encapsulated in there in one kind of object. So this is actually what makes that auto differentiation possible, is that you can feed it in different states rather than only having the step function available to you in OpenAI Gym. So certainly we actually have an interface to wrap a PalmDPs.jl model in an OpenAI Gym model. But since our model gives more access to it, you can't really go the other way. You could like create a copy of the environment at every step, but it's kind of a fundamentally different model. It's a fundamentally more expressive and more mathematical and less encapsulated model than the OpenAI Gym interface. Does that make sense?
Yeah, absolutely. Thank you.
Any other questions?
I don't want to dominate your time, but if I could ask a follow-up question.
Yeah, totally.
So that means that so you may have like problems integrating with, say, like external simulators. So you would never see something like the PyBullet environments that you see in OpenAI Gym and something like this, because you would have to explicitly model their state space, right?
Yeah. So yes. So you're talking about going the other way if you have a simulator, and so like There's another Julia package called reinforcementlearning.jl, which would be probably more appropriate for that. But yeah, so there are definitely Julia packages that are more appropriate for that situation where you don't have as much. It's more of a black box situation rather than a white or gray box situation. But having access to the state, or having this kind of range of different ways that you can interact with the model, allows you to use a lot more a lot bigger range of environments. So I'll give you a kind of a practical example. So one of the students in my class this year had this simulator, this satellite simulator, and he was trying to do Monte Carlo tree search with it. And you can't like reset that simulator. You have no access to the state. So what he had to do if he was at time step 10 or something and wanted to do Monte Carlo tree search forward into the future, he had to like start at time step 0 and simulate for 10 time steps, and then he would have that one like state available for him to simulate forward. So this access to the kind of state, internal access to the state dynamics is useful for allowing you to try more things algorithmically, but fundamentally you can't use algorithms that need that information on problems where that information is encapsulated. Does that make sense?
Yes, thank you.
So, I mean, I think this is like this is like gonna open up to a lot of more realistic cases, because in the real world, you do usually know something about the internal workings of the problem. You don't just have like a a simulator that you can't get any access into. You have some idea, like there's physics involved, so you know the laws of physics. So we want to exploit that if possible.
Any other questions for Zach?
I had a quick question. Is there a specific reason to use Zygote over the other AD packages?
Yeah, okay, so that's a good question. I don't know. I haven't like tried all of them. The reason that we use Zygote for this is because well, you should ask one of my students. But I think what I got from it is that in reverse mode differentiation, which is what Zygote does, it is more efficient for calculating the gradient of a scalar, quantity with respect to a vector input. Which is why it's used for deep neural networks, because you're trying to minimize the scalar loss and you have potentially a high dimensional input. There also is forward diff, but that's more efficient for going from a vector input to a vector output. And since we're just trying to maximize the value function, we decided to use Zygote because it's kind of a scalar output. But I'm not sure that it's the best thing to use. It's just the first thing that we tried.
Okay, thanks.